As we begin a new unit on atomic theory and structure, today's lesson is going to focus on the atomic theory that we know, specifically with a focus on the contributions of Bohr to the current quantum mechanical model of the atom. The concept of the atom dates all the way back to 400 BC, when Democritus, who was a Greek philosopher, was studying matter and things around him and realized that you could break things down, but only to a certain point, and that at some point all matter would contain small indivisible particles. And he is credited with the the term of the atom. Even though Democritus had the right idea, his theory was not believed for many, many years and went through some transitions until we got to John Dalton. So fast forward almost 2,000 years, and John Dalton, who was an English chemist, came up with some theories or statements about the atom. And considering the time period and the lack of, high quality equipment, he really got a lot of these things right. So he said that all matter consists of tiny particles called atoms. The atom could not be created, divided, destroyed, or converted into a different type of atom. Atoms of a particular element have identical properties. Atoms of different elements have different properties. And atoms of different elements combine in simple whole number ratios to produce compounds. All of this happens to be true, and he really sort of set the stage for the newer theory of the atom. 80 years later or so, J.J. Thomson started to do some experiments with the atom, and he thought that maybe there were smaller particles within the atom. And so Thomson set up a cathode ray tube that we see right here. And this is where he sent a beam of electricity through the cathode ray tube. I mean, they had electricity at the time. They just didn't know what was electricity made up of. And he put two magnets around the cathode ray, or the tube itself. And he noticed that the ray was either deflected or attracted to whichever pole of the magnet. And this told him that the electricity was made up of electron particles or negative particles. So he knew that there were negative parts to the atom. He assumed that there had to be positive parts as well, but he didn't really know the placement of anything. So he had this, as we call the raisin bun model of the atom, where these electrons, and again, he didn't know that they were protons, but he figured these positive charges would be scattered all through the atom. Ernest Rutherford came up with the most important experiment that contributed to our model of the atom, current model of the atom. So Rutherford decided to do some further testing on atoms, and he set up the gold foil experiment. And here he put an alpha particle, which is positively charged radiation that is coming from helium atoms, an isotope of helium. And he shot those positive particles at a piece of thin gold foil. Now, he figured that most of the positive particles would pass right through the atom. But instead, what he noticed was that some of the particles went straight through, but a few of them were actually deflected. And we see that here as well in the setup of the experiment. And what this told him is that the most of the atom was made up of empty space, but that there must be some positively charged regions that cause the deflections or the repulsions from this positive alpha particle here. So this became a revolutionary experiment because this came up with what we call the nuclear model, where the atom actually has a positively charged center that we call the nucleus. So the current model of the atom that you are aware of is the Bohr-Rutherford model. And this is named after Rutherford's discovery of the nucleus, but also Bohr's discovery of energy levels. And it has a nucleus in the center of the atom, and then it has our electrons that Thomson discovered scattered around the energy levels, but placed in a way that there is some order to it. We know that there's different energy levels that exist, And we know that those electrons are placed with a certain amount in each energy level. So Bohr's discovery of energy levels came from the many tests that he carried out involving hydrogen gas and running a current through it. Bohr's tests proved that these energy levels existed that were located around the nucleus, and that each of these energy levels were had a fixed quantity of energy, which we call quantization. And so this is where the term energy level comes from. It's a far better term than orbit or shell or ring, because it actually does prove that there are potential energies associated with each of these energy levels surrounding the nucleus. So Bohr's planetary model does show the nucleus in the center of the atom, similar to Rutherford's discovery. And then these energy levels that we see moving away from the nucleus. And you're going to notice that the distance that these energy levels exist at is slightly different, and they become closer together the further you get away from the nucleus of the atom. The potential energy of each of these energy levels and the locations within them, it increases as you move away from the nucleus. The nucleus is positively charged. Those electrons want to be as close to the nucleus as possible. So the further away you get out here, these electrons have high potential energy. So we know all this background. Let's just recap how Bohr came up with this concept of energy levels. So again, he took hydrogen and he subjected it to a very high electric current. And when he did that, he was looking at the gas tube that he was heating through a prism. And that prism scattered the light that was being created. And he noticed something called an electromagnetic spectrum that showed only 4 colors of light coming off of this gas spectrum. So we would be looking at this with a spectrophotometer, and we would notice this scattering of light. If you were looking at white light with a spectrophotometer, you'd notice all the colors of the rainbow. Here we only noticed 4. These 4 colors are significant because every color of light represents a different amount of energy or potential energy. And so when he saw these 4 different colors of light, he realized that the electron, because there's only one in hydrogen, was actually jumping to different energy levels that corresponded to the different light energies or the colors of those light energies. So we saw like a red and a purple. Red is associated with low energy, blue or purple is associated with high energy. So this is where we get, these concepts of, or these terms of, excited state and ground state, terms that we learned back in grade 11 applies here. Here's an example of the emission spectra of a variety of elements. So what we notice is that when we take samples of these elements and we subject them to high amounts of voltage and current, we notice that the electrons start to jump around. And this is the spectra that gets produced every single time. Okay, so we always notice the same lines of color, and we notice that they're not all the colors of the rainbow. That is significant because each of these colors of light are related to a specific energy. And this was telling us that these electrons were jumping around to different energy levels within the actual atomic structure. So to summarize the Bohr model, we know that there are these energy levels that exist, and this is from Bohr's little experiments with hydrogen. But a big problem of Bohr's model was that when we see multiple lines of the same energy, so for example, a couple of blue lines side by side, or 2 or 3 yellow lines side by side, his model did not account for that. And each of those lines represents a location away from the nucleus where this electron has jumped. So if you were seeing multiple lines of the same color, we know that something else is going on within the actual energy level itself. Now, to get us to, the extra piece within the energy level, we want to talk about some of the contributions and some of the theories that get us to this newer concept, or the quantum mechanical model. So Max Planck is a scientist that we credit for black bodies. Okay, so black bodies are when you take a sample of metal, often, and you heat it up and it burns or it glows an orange color. Okay, so Planck's discovery, right, was that energy, which appears to be emitted in wavelengths, is actually discharged in small little packets. Okay, so he figured this out, and they were trying again to explain this, like how could this energy sort of come in little packets or in little waves? Albert Einstein also contributed to the quantum mechanical model of the atom, and he came up with the photoelectric effect. And this is where electrons are emitted from metal surfaces when light falls on these surfaces. So this is like anything shiny, okay? When you see a reflection, Einstein knew that it was electrons that were being reflected or released or, moving away from the object. And Louis de Broglie, he stated that light and electrons have wave-like properties. So they're now starting to make some assumptions about the electron that we previously didn't know, and is helping us to explain sort of a newer model of the atom. In 1926, Erwin Schrödinger, a very well-known chemist, proposed what we call the quantum mechanical model. And this is where we now are saying that the electron has wave-like properties. And this statement describes, or helps to describe, why we would see multiple colors or multiple lines of the same color. These observations that Einstein and Planck and de Broglie had. And Werner Heisenberg, so a colleague of Schrödinger's, he also stated that it was impossible to know precisely where an electron is and what path it follows. And this is extremely important, because when we talked about the Bohr model, and if this is my nucleus in the center and we put one electron at the top and the bottom of energy level 1, and we started to put up, electrons at the corners sort of an atom, and then go back and pair them up, this guy is saying, we don't really know where those electrons are sitting. So this, again, is paving the way to this new quantum model. So what is going on then? Where are these electrons, and why is there something new that we needed to discover about them? So we now know that these electrons are actually not held in specific spots in an energy level, but they are held in locations, or what we call orbitals, that are actually within the energy level. And within each energy level, there are multiple orbitals where these electrons can be found. So as we look at each energy level, there is a correlation between the energy level number and then the number of orbitals that exist. So in your first energy level, you only have one orbital that exists. In the second energy level, you have 2 orbitals. In the third energy level, you have 3 green orbitals. In the fourth energy level, you have 4 blue orbitals. So you're going to notice the number, right, corresponds to the energy level that the orbitals are in. And then these orbitals have letters associated with them. So we'll see an s orbital, a p orbital, a d orbital, an f orbital, and they will repeat themselves as you move through the different energy levels. So we're going to do some more work on these orbitals, but until somebody comes up with a better model of the atom, this is the most current model, or quantum mechanical model of the atom, that we now are aware of.